So we didn't get to talk about this last time, but another way that you can have engines add heat is they can be at a constant temperature. So you can see right here we have basically a constant temperature heat addition. And then what we need to do is have something called a regenerator, which basically absorbs, and then you can like get the heat back. So I basically put heat out into the regenerator on this side and then bring it back in. The two cycles you would have is either constant volume or constant pressure, compression and expansion, and they'd be interfacing with this regenerator right here. And I thought it'd be kind of a nice introduction because today we're talking about the Brayton cycle, and one of the modifications that we'll see is you can add a regenerator. So the Brayton cycle is basically our model of the natural gas power plant or just some kind of power plant that relies on gas. So we're going to have things like the air standard, constant specific heats, all of that. So right here, this is what it's going to look like. Basically, we start by taking our air and we compress it, bring up its pressure, then we heat it up, then we bring it through a turbine. This is where we extract our work, and then we cool it down, and then we're back into this compressor. And this is basically, it just goes around in the cycle. I got the TS diagram right here. So the heat output is going to be the area under this shape, the net heat output, which is also going to be the net work output because the heat and the work have to balance because we're operating on a cycle. So real quick, if you just wanted to find things like Q in and Q out, we go ahead and do that. So our Q in, we're going to do per unit mass because we don't really know what mass. It wouldn't really make sense to even ask what kind of mass we have, right? Because we basically have a steady flow cycling through this power plant. We can't really say how much mass is there because there would just be really how much mass is flowing. We'd have an m dot running through each of these components. It's just going to be easiest to look at this per unit mass. So our heat in is going to come from this top heat exchanger right here. It's usually called the boiler or like the combustion chamber or something like that. I think the boiler is probably for a steam power plant because that's when you're boiling off the water, right? So since we're operating under steady flow, there can't be any change in the energy, which means that the heat input has to balance with our mass flow. So we're going to have H3 minus H2. So these are basically the quantities coming out and coming in, right? And this would be our CP times delta T for the power plant. And then our Q out, it's going to work exactly the same way. Our Q out, if we're looking at the magnitude, then T4 is going to be higher than T1. So this would be like H4 minus H1, which would be a CP times T4 minus T1. Instead of the compression ratio like we saw before, we're going to have the pressure ratio across this compressor. So we call this RP. And our RP is equal to basically P2 over P1. So the pressure from the output of the compressor divided by the pressure from the input right here. And if you go ahead and you do the thermal efficiency equals W net, which is Q in or minus Q out all over Q in. We did this before, and then you just replace this because we're talking about the isentropic compression and expansion across the turbine. Look at the engines if that's not making sense, but we went over it like 2 or 3 times, and it's the exact same process. So I don't think it makes sense to kind of go through it here. It's just a lot of the same math. This is kind of what happens once you get to this point. Is it's like a lot of things that you've already seen, and we're just combining them in new ways. It's a little bit of an info dump, and there's not really a whole lot of like, I guess, intuition. It's just like, here's what we're doing, here's what we're modeling, here are the assumptions we're making, here's what's going on, and that kind of happens when you're looking at an applied class. That's pretty much how it's going to be for the last few applications we're looking at. Anyway, our thermal efficiency is going to end up equaling 1 minus fraction 1 over our pressure ratio to the K minus 1 divided by K. All of this is in the power right here. Now in a real Brayton cycle, obviously it's not going to be isentropic, right? Our entropy isn't constant. Everything generates a little bit of entropy at least. And so instead of 2, we're going to say 2 isentropic, and we're also going to have a 2 actual. And the same thing from 3 to 4, we're going to have a 4 isentropic and a 4 actual. Across our compressor, we'll have 2 and then our actual states. And then same thing here for our turbine, right? And so we can do the exact same thing with our isentropic efficiencies. So for the compressor, basically how much work input would I ideally have to do divided by how much do I actually have to put in. So this is usually going to be a little bit higher, or in the best case scenario, it's equal to the isentropic value. So this is going to be H2S minus H1 over H2A minus H1. This is just an energy balance, right? We'd have heat input minus work output equals our delta H plus delta KE plus delta PE of the system. And I guess not of the system. This would be between the inflow and the outflow because we're looking at steady flow. Should be a little bit more careful there. And we're assuming it's adiabatic, which means that our W would be our delta H. Because we're dividing WS and WA, it doesn't matter if this is H1 minus H2S or H2S minus H1. As long as we're consistent in our numerator and our denominator, it doesn't matter. So anyway, we're going to get H2S minus H1 and H2A minus H1, which is going to end up being, Cp times our change in temperature, and then we cancel out our Cp's, and our isentropic efficiency just becomes this fraction of our temperatures. And for the turbine, it's the same thing, except now we're looking at the work output. So we want to know how much work output can we get divided by the best case. Again, this should always be a little bit less, or in the best case, it's equal to our isentropic work output. So same thing, heat in plus work in has to equal our delta H, delta KE, and delta PE. We assume that these are negligible in both cases, which means we just have our delta H here, which we replace with the Cp delta T, and then we cancel these out. So it just becomes a ratio of our idealized and our non-ideal temperatures. So in a practice problem or something, usually what they would give you is either these temperatures, which you may be able to also solve for with something like the K equations that we talked about. I'm not sure if I call them the K equations, but if you look back to when we started talking about entropy and all the equations we did for ideal gases, those work between states 2s and 1 and then 3 and 4s, and you can relate those to the isentropic efficiency using these equations. So depending on what they give you, you can go either way. And so now we're going to look at modifications to this cycle. The first one you can have is reheating and or intercooling. So the idea with this is that if you basically distribute your expansion across multiple turbines or your compression across multiple compressors, and then you cool it down or you heat it up in between them, you're going to be able to extract more work output. If we go down to the diagram right here, remember that basically we want to maximize the area under this shape. So instead of just going all the way up and then down and basically having our cycle, like if I go up here, this is our TS diagram, right? We went here, 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 and here. Basically, at the top, I'm going to do multiple turbine stages, and at the bottom, I'm going to do multiple compressors. You could theoretically do more and more and more, right? If you wanted to, you could basically get something going where you have like this down here, and then you have this up here. And as you do that more and more, this is actually going to approach the Ericsson cycle, which is one of the cycles we talked about at the very beginning, which is why I kind of wanted to show these, so because they're a little bit related, right? We have a constant pressure heat addition, then it's almost constant temperature as you get more and more of these reheaters and recoolers going in your system. But in a real world application, it doesn't make sense to add more than like one or two of these just because the cost of operating and the complexity isn't worth it economically. So yeah, that's it for the intercooling and reheating. There's not a whole lot. Basically, your Q in, well, you'd now have to have the Q in from 4 to 5. So I guess I can just go ahead and write this. Our Q in would basically equal our H5 minus H4, and then plus H7 minus H6, minus our H6. And then for the Q out, it's just going to be these guys right here. So our Q out would be H8 minus H1, and then you're going to add H2 minus H1, just like that. The pressure right here is basically going to be the same for each turbine. So basically, the turbine pressure drop is going to be the same, and then the compressor pressure changes is also going to be the same. So you can kind of draw this horizontal line between these states right here. And then this regen right here, that's the next mod we're going to talk about. See if I go down here, we got the regen mod. But if you wanted to combine them, basically what would end up happening is that you would have your regenerator go to this temperature right here. I'll just go ahead and break it to you now. The idea of the regenerator is that our exhaust temperature from this turbine is a little bit higher than it would be before we sent it into the boiler. So the idea is instead of just getting all of this waste heat out, we can save some of it by preheating this. That way we don't need to add more Q in our combustion chamber, which means that we're going to be able to get the same amount of work output for less Q in, which means that we have a more efficient power plant. So this temperature difference right here is what's created by the reheater, the combustion chamber, or whatever. So your regenerator would be able to give you all of this heat that would normally be done in the combustion chamber, and then your combustion chamber would only need to do this little bit. So that's if you wanted to combine the two mods, but usually you're just going to see one or the other. So now we can go ahead and look at the regen mod in its full. So like I said, compressor goes into our regenerator, which is just a heat exchanger, combustion chamber, and then we've got our turbine out and out to here. Now, if you notice, basically I've numbered this so that we have 1, 2, 3, 4 is our normal cycle, but then we've also got this 5, 6, and then you'll see different notations depending on which book you're looking at. So for example, I remember seeing it in a lecture where this was like 7, 8. I think the book has like a 5 prime or something. I put A's there just because I think that makes the most sense, because basically what you're looking at is the ideal versus the actual. So in the ideal case, theoretically what you could get is if you're coming in at state 2 here, right, this temperature down here into this side of the regenerator, and then you also have state 4 coming in from your turbine, theoretically you could basically transfer all of the thermal energy from here to here and get this up to the same temperature as this, and then this would basically swap down. So 2 would go to 5 and 4 would go to 6. But in reality, you would normally need like a temperature difference to do that. So they're going to be closer to basically equilibrium. You're not going to be able to save as much heat. You're not going to be able to, right, save it as it's going to here. You're going to need to have more done by the boiler. So this is our ideal case, and then this is our actual case. And the thing that relates to those is a quantity called the effectiveness. It's epsilon. So this is basically our Q regen actual divided by our Q regen. How much we actually, I guess this would actually be our real, and then divided by our ideal, because our real is going to be slightly lower. Right, so this would equal H5 minus our H2 divided by, and then this would be H5 actual. But H5 actual is actually just going to be the same as H4 because we're transferring all of that energy from the exhaust in the ideal case. So this would be H4 minus H2. So big point here for the thermal efficiency is that our Qin would normally go from 2 to 3, but now our Qin is basically only this. So another way you can think about this is we can get our Qin is 2 to 3, and then subtract Q regen, which would be our H5 minus H2. And the way to relate those, if you're not given enough information, like you're not going to give in every single state of this power plant, is you'd use the effectiveness right here. Now, one more thing I forgot to mention about this cycle is there's a quantity called the back work ratio, which is like a real quantity that you'll see in industry. And basically it's the ratio of how much work input you need to put into the compressor to how much work output you're getting from the turbine. So this is work compressor over work turbine. And in some cases it can get pretty bad, especially for a gas power plant. Like sometimes even a third of your work is just going to fueling the compressor. That's just kind of one of the issues with the extracting it as a gas, is you can't take full advantage of the different states. And so real quick, as a bonus, I just kind of wanted to show you this right here is basically the engine of a rocket. So the idea is that you have air coming in here. This is kind of like a diffuser. It's going to increase the pressure. I know I kind of have it drawn as a nozzle, but this would kind of theoretically be a diffuser. Then you'd have your compressor right here, which is like the fan that's increasing the pressure, and this goes into the combustion chamber, which heats it up. Then you got the turbine, which extracts some of the work in order to propel, the fluid out of here. You've got a nozzle to increase the velocity a little bit. That way the jet can actually fly, and then a little bit of that work goes into fueling all the electronics and things like that.